Okay, in this video, we will briefly overview the three layers of complexity towards which we will discuss the theory of the possibility of learning. We will first consider the reliability of assessing a hypothesis. So we will introduce a theorem which states that if we have sufficiently many training examples and evaluate the performance of a hypothesis on such a set of training samples, then the evaluated in-sample error will track the corresponding out-of-sample generalization error. So, which means if the example in this dataset is sufficient, and for some criteria, we evaluate that some H on the hypothesis, then the evaluation will reliably or with some probability to track, with sufficient probability to track the hypothesis would be performance on the generalization as the generalization error. So this is to say, if the hypothesis works well on the training dataset, it is unlikely to fail in generalization. It sounds perfect. It sounds just what we need, but is this theoretical guarantee of evaluation on a hypothesis sufficient? No. We notice that this theory is about the reliability of evaluation of a hypothesis. However, what we are concerned is to assessing the result of a learning process. We are concerned with the hypothesis that is selected by a learning algorithm from a family. So straightforwardly, you might think that how about let us to apply the theoretical guarantee on the evaluation reliability of individual hypotheses and just have because the previous hypothesis saying that for sufficient sufficiently large training set, we have some guarantee. Then how about we have an even larger training set so that we want to have a guarantee that every single hypothesis won't in the hypothesis family. If we put the probability that any one of the hypotheses in the family will get a large generalization error together, we have this sum of possibilities shrink to a smaller probability by increasing the training data set, the size of the training data set. This is a viable approach, although very brutal and not so efficient, but it's viable. When we are considering two hypotheses, say if we have seen that the probability of get a bad generalization for a single hypothesis is some, for example, p. Then if you have two hypotheses, for any one of them to get a bad generalization, you have at most the probability of 2p. If you can get p as small as you want, then by the same line of thought, you can get 2p as small as you want. And following this line of thought, you can get 3p, 4p, 100p, 1000p, whatever kind of np as small as you want. But unfortunately, for any useful hypothesis set, for example, the perceptions or the decision trees, all this kind of practically useful hypothesis family, they all contain infinitely many hypotheses. So you do not have some fixed n so that you can, by reducing p so that np is as small as you want. As n is infinity, so however small you get p, it is not sufficient to guarantee the np is within some limit, reasonable limit. Therefore, in the second step, we will invent a finite delegate of the event that any hypothesis in the hypothesis family is a generalization error on the unknown data set will not different from the training set error too much. This statement inherently infers to check for infinitely many hypotheses, which we cannot afford. We will invent another statement. This statement, although it refers to all members in the hypothesis set, but it does not refer to the unknown distribution. It uses another delegate for that, for which we will be able to categorize the hypothesis family into limited groups, for which we will be able to reduce p so that the limited factor, let's call that m, this mp will reduce as we want. We establish this finite delegate by looking at the link between when we do logic derivation with regard to event sets and the associated probabilities about those events. So we state the relationship, logical relationship between some events, and we consider how the logic derivation implies which event set is larger than the others, and therefore we establish the relationship between their associated possibilities. So that is the second step. This step is a bit technical, but you won't have a large gap between each derivation steps. So if you pay enough attention, I think you can get over this. But you don't, just keep in mind, now we can deal with a finite number of possibilities that things go wrong. And then we can limit each individual of those going wrong probability so that the total probability of things go wrong is limited. So that is the plan. Thirdly, it turns out that the delegate we employed in the previous step, unfortunately, although it is finite, it grows with the number of the training data set. So as we have said, when we increase the size of the training data set, we will reduce the risk of an individual hypothesis have large difference in the in-sample and out-of-sample evaluation. So the bad thing happens, this individual bad thing probability reduces. However, our finite delegate, although it is finite, but the particular number of groups also with the number of samples in the training set. Therefore, the individual risk reduces, but the number of ways in which we can incur those risks increases. There is a competition of these two risks. One increase, one decrease. When we put them together, of course, we want the general risk decrease with respect to the size of the training samples. Then in the third step, we put everything together and we find that with some condition, we will have with some condition on the hypothesis set, we will have the learning process will converge. The risk of the learning process will converge to some limited size, and we can get as reliable as we want when we increase the number of training data samples. So that is our plan.